Hello everyone, welcome to a lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Comsets University, Islamabad, WA campus. The topics that I'm going to discuss in this lecture are processor control instructions and control transfer instructions. These are the two types of instructions in the instruction set of Intel family of microprocessors. There are other types of instructions as well, like arithmetic instructions and logical instructions, string manipulation instructions, and etc. But only these two types of instructions would be discussed in this lecture. The slides used in this lecture have been edited from the two sources given here. Processor control instructions are a set of instructions that are responsible to control operations of the microprocessor, or in other words, to control the status or the values of certain flags of the microprocessor. These flags are in the flags register of 8086 microprocessor, or E flags register of 80286 and above microprocessors. Apart from changing the status of the flags, there are other instructions as well that monitors certain pins of the microprocessors. Starting from the first instruction in this set, STC means set carry flag. So this instruction is used to set to 1 the value of the carry flag in the flags register of 8086 microprocessor. This value is not only checked or set by this instruction, but there are arithmetic instructions and logical instructions. They also change the values of the flag bits. The carry flag may also need to be cleared, and for that there is an instruction CLC, that means clear the carry flag. So this instruction can be used by the programmer to clear or set to 0 the value of the carry flag in the flags register of the microprocessor. There is a third instruction as well, CMC, that means to complement the value of the carry. So the carry flag is complemented by this instruction. This means that if the carry flag is already set, this instruction would clear it, and if it is already clear, this instruction will set it. So these three are the instructions used to monitor or to change the value of the carry flag. And as I said, there are other assembly language instructions, arithmetic instructions, logical instructions that they also change the value of the carry flag depending on the result or the result of computation by those instructions. There is another important flag bit in the flags register called direction flag, normally represented with DF, or in certain books it is represented with D. So DF means direction flag. Direction flag is very important flag, in particular used in string manipulation instruction. The value of this flag sets auto increment mode when the value of D is 0, or auto decrement mode when the value of D is 1. So it sets the auto increment or auto decrement mode used during the string manipulation instructions. In the string manipulation instructions, there are two registers, index registers, destination index and source index registers. These index registers are automatically incremented or decremented depending on the value of the flag, this direction flag. So whatever the direction is desired, that can be achieved by setting the value of the D flag to 0 or to 1. STD sets the value of the direction flag to 1, and similarly there is an instruction that clears the direction flag to 0. So these two instructions are used to set or clear the direction flag, or in other words, to set auto increment mode or auto decrement mode for incrementing or decrementing the index registers used in the string manipulation instructions. Similarly, there are two instructions for controlling the interrupt flag, IF interrupt flag. So STI sets the interrupt flag or enables the interrupt flag. When interrupt flag is 1, then interrupts are enabled, and if the interrupts are to be disabled, then CLI, which means clear interrupt flag, instruction is used. So this instruction would clear or set the value of interrupt flag to 0. So interrupts would be disabled as long as interrupt flag is 0. Okay, then there is a no operation instruction. This instruction does nothing, as the name specifies or the names indicates. In earlier microprocessors or in earlier programming, this instruction used to be used for adding delays, because this does nothing. So adding it a number of times, microprocessor would spend a small amount of time on executing this instruction, and that would aid that unit of delay. And if longer delay was desired, then this instruction was used many times, and sometimes in loops. Another purpose of this instruction was to aid this instruction in programming, and that is just to keep space for future instructions. Nowadays, this instruction is not a very good calculation or source of adding delays, because the delays are not that much accurate. Halt instruction stops execution of the software when the interrupt is set. If interrupt is set, then this instruction will stop executing software until an interrupt happens. Wait instruction monitors test or busy pin of the microprocessor. And 8086 and 8088 microprocessor, there is a pin test, and in the later microprocessor, this pin was replaced with busy pin. So wait instruction waits for the test or busy pin to get active. That means that it returns to 1. If it is 0, then it waits until it returns to 1. Escape instruction passes instructions to coprocessor, which also shares the address and data bus with 8086 microprocessor. Lock instruction is used as a prefix before some instructions to lock or disables bus for the duration of the instruction. And if a number of instructions are prefixed with lock prefix, then bus is disabled for the execution of those instructions. Control transfer instructions is another set of instructions in the instruction set of 8086 microprocessor. Control transfer instructions are responsible to skip a section of program and branch or jump to any part of the memory for the next instruction to be executed. So normally microprocessor executes instructions of the program in a sequence, starting from the first instruction. Each time when an instruction is being executed, the microprocessor maintains the address of the next instruction to be executed, which is next to the instruction currently being executed in the program. and this order is set by the programmer while writing the programs. But uh, instead of the sequential execution, there is a set of instruction as well to change the flow of control from sequential to any other location. Control transfer instruction exactly do that. So in control transfer instructions, there are conditional jump as well. A conditional jump instruction allows decisions whether or not to jump based upon numerical test using compare and test instruction. The result of such instructions that perform numerical computation or numerical test is stored in the flags bit and the flag bits, and then those flag bits are then tested by conditional jump instructions, and based upon the result of those flags, whether or not a jump is taken to another location inside the memory. Loop and conditional loop are also forms of jump instruction because they also cause the flow also controls the flow of program execution. As I said, control transfer instructions are responsible to direct the flow of a program and allow the flow to change. These instructions transfer the control to a specific destination or target instruction in the program, and it also the change in flow occurs after a decision made with a compare or test instruction, and these instructions do not affect flags. Other instructions like arithmetic and logical instructions affect flags, but these instructions are not affecting flags. Control transfer instructions are only making decisions upon the values of the flags affected or changed by other instructions, but they themselves do not change the values of the flag bits. And control transfer instructions in 8086 in particular, unconditional transfers can happen in three forms. There can be a call to a subroutine. A call instruction is CALL followed by an address of the subroutine or name of the subroutine. The name is provided through a register, or it can be provided through a memory location, or it can be directly provided through a displacement, which is in all of these forms, the address of the subroutine is provided. So call instruction would transfer the control from the existing or the current routine to this calling routine, and after some instructions are executed in that subroutine, subroutine is a unit or set of instructions to perform a specific task. So after all the instructions in that subroutine are executed, there is a return instruction, RET. So this return instruction would change the flow of control from that called routine to the the caller routine from where this call was executed. So uh, call and return instruction works together. The subroutine is to be called using the call instruction, and from that subroutine, the control has to return back to the original routine using the RET return instruction. So both of these are forms of unconditional transfer or conditional jumps, but there is a specific jump instruction as well, represented with JMP. So this is the mnemonic of jump instruction, and of course for all these instructions there are opcodes, binary codes to represent them in the memory. So jump instruction is also followed by either a register or a memory location or 8-bit or 16-bit displacement. All these are addresses of the location or the address of the instruction to where the jump has to happen. So jump means that the control has to transfer, but to where? That address is provided by through a register or through a memory location or through 8-bit or 16-bit displacement. Unconditional jump, JMP, is very important instruction used by programmer. So this instruction would cause the control to the flow of control from one place to another in the program or in the memory. There are three types of jump instructions, unconditional jump instructions. By unconditional, we mean that this jump will always happen without a condition, without checking a condition. So whenever this instruction is used, jump will always happen. There is another set of jump instruction called conditional jump instruction, and conditional jump instruction always check a condition. If the condition is satisfied, the jump will happen, otherwise the jump will not happen. But this jump is unconditional. This will happen anyway. So depending on the range of jump, the number of instructions that are skipped or the number of bytes that are skipped from the current location, based on that range, unconditional jump are of three types: short jump, near jump, and far jump. Short jump is a 2-byte instruction that allows jumps or bronze to memory locations within plus 127 till minus 128 bytes. In the 2 bytes instruction, 1 byte is the opcode or the operation code, and 1 byte is a sign number or sign displacement that has a value, and that value represent the number or indicates the number of instruction, the number of bytes that are to be skipped, and the value is the displacement is sign number. So if it is negative, then the jump is backward in the backward direction, and if the number is positive, then the jump is in the upward direction, in the direction where the memory addresses are increasing. And each time the jump happens, the jump is from the address following the jump instruction. So whenever the jump instruction is being executed, the current location is the location of the next instruction, which the address of which is maintained in the instruction pointer. Near jump is a 3-byte jump. It allows a branch or jump within plus minus 32 kilo bytes from the instruction in the current code segment. So from the current location, in the near jump, which is a bit longer jump than the short jump, the jump will skip 32 kilo locations in the backward direction or 32 kilo locations in the upward direction. So this jump will cover the entire code segment, because the entire code segment in 8086 when operated in the real mode, or later microprocessors when operated in the real mode, the segment is 64 kilobytes. So this plus minus 32 kilo jump is sufficient to cover the entire code segment. And then there is a 5-byte par jump. This jump allows a jump to any memory location within the real memory system. So we will see shortly that the short and near jumps are often called intra-segment jumps, because these two jumps can allows the program control to transfer to any location inside that existing segment, code segment. The range of the short jump is short, from plus 127 till minus 128, so it covers in total 256 bytes. But near jump is longer and it covers the entire segment. But every time these jumps happen, the control transfer to within that existing segment. So that's why these two jump instructions are also called intra-segment jumps. While in the case of par jumps, the jump happens from the existing segment to any other code segment, and that's why it's called inter-segment jumps, because the jump happens between the two segments. These are the bytes of the three types of unconditional jump instruction. Short jump is a 2-byte instruction with the operation code is a single byte, and the operation code of the short jump is EB in hexadecimal. So this 8-bit value is stored in the memory to store the short jump instruction, and this opcode is followed by an 8-bit signed displacement, and this signed number would give us a value ranging from 127 till minus 128. So, for example, if the value of this displacement is 20 plus 20, then the jump will happen in the upward direction or in the forward direction, skipping 20 bytes between the existing location from the existing location. A near jump is a 3-byte jump with the E9 is the operation code of the near jump, and this near jump opcode of the near jump is followed by 2 bytes displacement, sign number displacement, and the low byte or the least significant byte is on the left hand side, and the high byte or the most significant byte of this displacement is on the right side. So this is a 16-bit sign displacement, and this 16-bit sign displacement would provide the address of the next instruction to be executed. And finally, for jump is a 5-byte jump. So these are the 5 bytes of the for jump. EA is the operation code of this jump, and the next 2 bytes after the opcode of the for jump represent the 16-bit value of the instruction pointer. This 16-bit value is the new value of the instruction pointer, and after the 16-bit instruction pointer value, there is a code segment value. So this is also a 16-bit number that would be the new content of the code segment. And remember, they're just like the near jump. The low byte is arranged in the left side, and the high byte is arranged in the right side. So in the instruction pointer content, the 16-bit instruction pointer content is organized as the low byte is on the left hand side and the high byte is on the right side. Similarly, in the code segment, for the code segment value is organized as the low byte is on the left side, the high byte is on the right side. So these 4 bytes would provide the new content of the instruction pointer and the new address of the new content of the code segment register. Short jump, more about short jump and these 3 types of the unconditional jump. Short jump is also known as relative jump, as they can be moved with the related software to any location to the current code segment without a change. So each time this jump happens, the jump happens relative to the existing location of the instruction, the jump instruction. So that's why this jump is also called relative jump. The jump address is not stored with the opcode, but the displacement or distance is stored with the instruction that is followed, that follows the opcode or the operation code of the jump instruction. The 1-byte sign displacement, whose value ranges between plus 127 to minus 128, as I explained in the earlier slides. So this is a simple example of the short jump where the memory locations or the memory addresses are also given. So in case of a short jump, when the microprocessor executes a short jump, the displacement which is followed after the opcode is sign extended and added to the existing or the current content of the instruction pointer or extended instruction pointer to generate the jump address within the current code segment. So by default, the current code segment, the segment address, the segment is the current code segment. So the microprocessor knows that the jump happens inside the existing segment. So the instruction branches to this new address for the next instruction in the program. So here is an example where the memory addresses, the physical addresses 1000, 100001. These 2 bytes stores a short jump, because we just saw that a short jump is 2 byte long. So this JMP is a mnemonic of the jump instruction, but instead of this, in the memory, in the actual memory, E8, which is the opcode of short jump, would be stored, and this opcode is followed by an 8-bit displacement. In this case, it is +4. So this +4 and this opcode of the instruction are stored in these two memory locations. While this instruction is being executed, the instruction pointer has a value of the next instruction, which is stored here, and the instruction pointer value is 002, and the existing code segment is defined at 1000. So just like other physical addresses generation, each time the physical address of this instruction is generated, it is generated as follows. The 16-bit value from the code segment is left shifted by 1 hexadecimal digit. So existing value of code segment is 1000. So another 0 is added on the right side, that is equivalent to left shifting by 1 hexadecimal digit. And this 5-digit value is then added with the current content of the instruction pointer, which is 0002. After these two values are added, we will get 10002, which is the address of this next instruction. So this is how the address of the next instruction, the physical address of the next instruction, is calculated by the microprocessor. So if the execution would continue in sequential order, then when this jump instruction is executed, this would be followed by the executing this instruction stored at 1002. But as this instruction is a jump instruction, it will cause the flow of control to change from this instruction to here. And how is that happen? It is it is computed, or this jump happens as follows. So the new content of the instruction pointer is calculated, and that is calculated by adding the existing value of the instruction pointer plus the displacement of the jump instruction. So the displacement in this example is 4. So 4 is added with the existing content of the instruction pointer, which is 002. So 002 and 4, they are added, and we will get 006. So the new content of the instruction pointer is 006. The code segment is existing code segment, so it is 1000. So to calculate the physical address of the next instruction to be executed in the existing code segment, this code segment value is left shifted by 1 hexadecimal digit. So we will get 1000 and another 0, and then this new instruction pointer value is added with this computed value, which is the starting address of the code segment. So we will get 10006. So this is the new address from where the next instruction is to be fetched and executed. So the displacement is 4. So from the existing location, which is this 1, 2, 3, and 4, these 4 bytes are skipped in the forward direction, because the displacement is positive number, so the jump happens in the forward direction. If this displacement would be negative, then the jump would happen in the backward direction, in the direction where the memory addresses are decreasing. When a jump references an address, the displacement, which was 4 in the for the previous example, normally that is not the practice. The jump address is provided through a label, which normally identifies the address to where the jump has to happen. So, for example, the jump next instruction is an example. It jumps to label next for the next instruction. It is very rare to use an actual hexadecimal address with any jump instruction, because hexadecimal addresses are difficult to remember. So that's why instead of providing the actual hexadecimal address of the jump, labels, which are English names of the location or the address where the jump has to happen. So labels are easy to remember by the programmer. So that's why the normal practice is to use labels in the program. The label next must be followed by colon. So for example, in this style, next followed by colon to allow an instruction to reference it or to call it. If a colon does not follow, you cannot jump to it. So for the label, it is important to use a label and then use a colon after the label. The only time a colon is used is when the label is used with a jump or call instruction. Near jump, a near jump passes control to any an instruction anywhere in the current code segment, and the displacement provides the value in the range from plus 32 kilo to minus 32 kilo bytes, and this range is from the existing location of the instruction pointer, just like we saw in the case of short jump. So the distance is plus minus 2g in the 80386 because the segment in the 80386 and above can be 4 gigabyte when they operate in the protected mode. When these microprocessors operate in the real mode, the segment is the same as 8086, which is 64 kilobyte. But when these microprocessors operate in the protected mode, the segment size can be 4 gigabytes. So for that, the distance needed is plus minus 2 G bytes. I remember that in 8086 and 8088 microprocessor, the only mode is the real mode. So each time the segment is always 808. In these microprocessors, the segment size is 64 kilobyte. So 16-bit displacement is sufficient to jump to anywhere in the code segment of the 8086 and 8088 microprocessor, or in the later microprocessor when they operate in the real mode. If they operate in the protected mode, then the segment can be larger, up to 4 gigabytes. So plus minus 2G jump is needed to cover the entire segment. So near jump is a 3-byte instruction with opcode, which is a single byte opcode followed by a signed 16-bit displacement. The sign extended displacement is added to the instruction pointer, just like the short jump, to generate the new jump address. Because sign displacement is plus minus 32 kilo, a near jump can jump to any memory location within the current real mode code segment. And remember that the addresses in the memory are cyclic in nature. So the next address of the last address of the segment is the first address of the same segment. For example, if the jump instruction is on the last memory addresses of the last addresses of the segment, and it is a near jump or short jump, and if the jump is 1 byte in the forward direction, then the program control will flow to or jump to the first address of the same segment, because the addresses are cyclic in nature. The next address of the last address of the segment is the first address of the same segment. The protected mode code segment and the 80386 and above can be 4 gigabytes long, as I just said. 32-bit displacement then allows a near jump to any location within the plus minus 2G bytes. So this plus minus 2G bytes range is sufficient to cover the entire 4 gigabytes segments in the protected mode. Here we have a very simple example. So let's assume that these 3 addresses store a near jump instruction, and the mnemonic of the near jump is the same as the short jump, JMP, but in the actual memory, different opcode, which is E9, would be stored in the memory, and that is sufficient for the microprocessor to interpret it as a near jump. This opcode is followed by 2-byte signed displacement, and this is the low byte and this is the high byte of that displacement. So the value of this displacement is 0, 0, 0, 2. So this is the displacement, and at this time when this instruction is being executed, the next instruction that the microprocessor stores the address of is stored here. So at location here. So this is the instruction which is to be executed next. If this would not be the jump instruction, if this would be any other instruction, then this microprocessor would fetch this instruction. So currently, the microprocessor stores the address of next instruction, which is here at location 1003. So that's why the current content of the instruction pointer is 003, and the segment is again the same segment defined at 1000. So the new jump address is calculated by adding the existing address, the current address of the instruction pointer, which is 003, and the value in the displacement, which is 002. So when 003 and 002 are added, the new content of the instruction pointer would be 005. So this 005 is added with left shifted value of the code segment register, and a new physical address is calculated, and that new physical address is 10005, which is the address of the next instruction to be executed. As the displacement value is 2, so these 2 bytes in the upward direction are skipped because this value is plus 2 plus 0002. So these 2 bytes are skipped in the upward direction. As I said, if this would be a negative value, then the jump would happen in the backward direction. Near jump is also relocatable, just like the short jump, because it is also a relative jump. By relative, we mean that the jump happens relative to the existing location. So if the existing location, the location of the jump instruction is changed by copying or storing the same program in at different memory locations, then the jump address would also be changed because the jump happens relative to the existing location. So this would provide, this would allow the whole program to be relocatable to anywhere in the memory, and the jump location or the jump address or the jump range will not be disturbed, because if the jump from the current location is 8 byte in the upward direction, and when this program is reloaded to another memory location, the same relative address will remain in its place. So the jump will work even if the whole program is stored and then in any other part of the memory. This feature is called relocatable or a relocatable program. And this feature, along with the relocatable data segments, Intel microprocessor is ideal for use in a general purpose computer system, because in a general purpose computer system, a program might be loaded in one location today, but tomorrow it may be loaded in another part of the memory. And as the jump addresses are relative to the existing location of the jump, the overall function or the operation of the jump instruction will not change, and this is the success of the Intel family of microprocessor, because software can be relocated from one location to another. So software can be written and loaded anywhere in the memory, and they can function without modification because of the relative jumps in relocatable data segments. Thank you.